Welcome back, everyone. Today we're going to be solving LeetCode's weekly contest 359. I shared the link in chat, and these are the 4 problems, the 4 questions as they call them. And some people solve them very quickly, and I'm impressed. Less than 7 minutes. That's crazy. Anyways, we're gonna explore different ways of thinking about the problems, different solutions as we usually do, maybe faster solutions than necessary for making connections between concepts. So let's get started with Q1. I'll share the link. So check if a string is an acronym of words. Given an array of strings, words, and a string S, determine if S is an acronym of words. Okay, I guess that's pretty self-explanatory, but here we get a more precise definition. Let's consider an acronym of words if it can be formed by concatenating the first character. Yeah, the fun noise, I try to eliminate it beforehand, but I couldn't, so bear with me. This is the best that I could set it up for now. I'll try to fix it in future streams. I can try to increase the gain. Is it better or worse now? I think it might be worse, but maybe my voice it's clearer. Is it better or worse? Give me a bit of information, Lucia. It's okay. Okay, you didn't answer the question. Well, let's move on. So yes, to be an acronym of words mean that if you take the first letter of every word, that is the acronym of words, and you want to check if S is equal to that. So this is a kind of just do it kind of problem. You have to do what you're asked to do pretty straightforwardly, and the constraint don't even matter, because you don't even need to iterate the words, you just get the first character. So without further ado, let's code this. We want to know if S is equal to, and let's go over the words in words, and you get the first letter, and we want to create a string out of this, which you can do with join in Python. This should be good enough. I'm pretty confident, so let's submit without even running the code. How crazy is that? Okay, accepted. So yeah, no, not much to say about this one actually. Different languages will have different ways of doing this, but essentially you want to create the acronym as it is defined here and compare it with S. So Let's move on. Second problem, or Q2. Determine the minimum sum of a k-avoiding array. K-avoiding, that's interesting. You're given two integers n and k. An array of distinct positive integers is called k-avoiding. It's called a k-avoiding array if there does not exist any pair of distinct elements that sum to k. Turn the minimum possible sum of a k-avoiding array of length n. Okay, so they give us only numbers, and we want to find an array of size n, but we only return its sum. Okay, I'm getting a feel for the problem. It's good to start reading the problem. Well, the constraints are interesting. These numbers are very small. They're only like 50 squared different inputs. And we can see some examples. And they even give you the array. One, two, four, five, six. So they're skipping 3. The sum is 18, and they say that it is. They say that it can be proven that there is no k-avoiding array with sum less than 18. All right. This is even a smaller case. And 1 and 2 is the answer, which is obviously the least it could sum, because remember that these have to be distinct positive integers. So the best you could do is have the numbers from 1 to n consecutive. All right. So the first impression here that you can get when you read this is it's called a constructive problem, when you need to construct a solution, like an object that is optimal in some sense, and it's easy to get overwhelmed by how many options, how many possibilities there are. So one strategy to deal with that is to try to constrain the possibilities. So let's start by thinking about particular numbers. Sometimes a way to constrain the possibilities is to look at extremes. And my intuition is to go to the big numbers. So what if you have a big number, a number much bigger than k, then it cannot be paired. Whatever pair you find for it, since it has to be positive, it's still going to be greater than k. So you don't have any restriction for that kind of big number, but it doesn't even have to be too big. Even if it's equal to k, that condition stands, because if you have k, whatever you add to it, you're going to have a number that is, even if you add 1, you're going to have a number bigger than k. So that's the first observation. For the numbers that are greater than or equal to k, you don't have any restrictions. And of course, to minimize the sum, you want to get the least number. So we don't know if we're going to need to add numbers from this range, but if we do, we want to get k, k plus 1, k plus 2, and so on up to whatever amount we need. So that's the first observation. What happens for the numbers that are between 1 and k minus 1 inclusive? So let's say that we take 1, which is the minimum. When we take 1, then we know what the pair that adds up to k is. This is similar to the concept of the two-sum problem. We have an equation, we want to find another number that adds, when you add to 1, it's k, so that's k minus 1. And that's true for whatever x you have. If you have x, when you add it to k minus x, you get k. So whatever number you choose, the pair that adds up to k is determined. There's only one. So between these pairs, we want to choose the minimum, the smallest one, to minimize the sum. So that means that we want to choose 1, 2, 3, and so on up to the middle, up to k divided by 2. And k divided by 2, if k is even, that's okay. We can take k divided by 2. For example, if k is 4, we can take, in this example, we can take 2. Because we cannot pair a number with itself. So it's valid. So we want to take all the numbers from 1 to k divided by 2 with integer division, inclusive, and then we need to skip all the numbers that come after that and continue from k, as we said based on our first observation. So given that the numbers, that there are only 50 numbers, we can do this pretty straightforwardly without worrying. Hey Sam, thanks for the follow. We can do this straightforwardly. So we need to choose n numbers. Okay, so we iterate n times. We're gonna return the sum, and we want to, we have like 2 cases. Okay, let's do them 1 based. Why not? For convenience. So we want to have 2 cases. We said that if I is less than k divided by 2, then we just want I. But if it's greater than k divided by 2, we want to make a jump to k. Okay, so here we want from I is going to be this. Okay, so if we subtract this from it at the minimum, so if this subtract this from k, we're gonna have the numbers from 0, and then we add k, and that should work. It's a little bit odd that we have k 2 times, but it solves this example. We only have 1 example now. Why don't we have, okay, I deleted it. Okay, so it works. So I did this very methodically. What I did was the minimum I that doesn't satisfy this condition is k divided by 2 plus 1. So if I subtract that from I'm gonna get the numbers from 0, 1, and so on, and I want them to start from k because of what we said before. So that's how I constructed this expression. So I'm being very methodical. That is the idea behind this stream. Okay, so that works, but this is the order of complexity is linear in terms of n. Okay, but we can do better. We don't need it for the contest because they're only, well, we know that n is up to 50, but for learning we can do better. And let's go to the drawing board and see. You might realize that here we're adding the numbers from 1, 2, 3, 4, and so on, which is the sum of the natural numbers. You've probably seen that before. There is a formula for that. But the catch is that we then are adding the numbers from k and then k plus 1. So it's also a sum of consecutive numbers, but it's not quite the same as the one that starts from 1. So this is a generalization of the sum of the natural numbers. But let's start by thinking about these numbers from 1. Forget about now about the problem. Let's think about this. Maybe you already know this, but maybe this is a different way of thinking about it. Let's say you want to sum the numbers from 1, 2, 3, 4, 5. So this is 2. I'm making it visual to help your intuition. So yes, let's say that here this is 1, 2, and so on. So this is why these numbers are called triangular, because it's a kind of a triangle, this, or it's a stair. And one way to do this is to think about one way to derive the formula for this. I don't want to memorize it. I want to derive it in a visual way. And maybe we could, what is the midpoint in the y-axis? It's 5 plus 1 divided by 2, which is 3. So this is the midpoint, and that means that this excess here, which is in this case, in this example, is 3, it's equal to 3. It's the same as what's missing here, right? Because this is symmetrical, because we define this as the midpoint. So that means that you could visually move these 3 points into here, and now you have a rectangle. Okay, and rectangles are easy. to count. Okay, so let's count this rectangle. This is not a US flag, by the way. It's just that this this application limits the trial version to 3 colors. Anyways, so then in this case we have, I'm going somewhere with this, don't worry. So we have 5 things. The base is 5 and this is 3. So this is 15. Okay, and if you check it out, this is 6, 10. Okay, it matches. But what we did, 5 could be n, and then what we did to get the midpoint was n plus 1 divided by 2. So we have derived the formula of n times n plus 1 divided by 2. But what if we don't start from 1? What if we start from another number? Then it's the same thing, same idea applies. We get, let's say we start from a, so this is higher than 1, but then we have a plus 1, a plus 2, a plus 3, and finally b. Don't bear with me, I'm not good at drawing here, but so now let's apply the same logic. The midpoint, instead of here we assume that the minimum number was 1, but in this case it's a, so and n corresponds to b, so it's a plus b divided by 2. That is the midpoint. And the number of elements, before it was n, but here it's b minus a plus 1, right? Because in the edge case where a and b are the same, b minus a is 0, but we have 1, so we have to add 1. So that's by the way, that's a good way sometimes to test a formula. Look at the edge cases, try it out. Okay, so now we have the formula for this kind of sum of consecutive numbers starting from some arbitrary a and a bigger number or a greater than or equal number b. These are called, by the way, these are called the triangular numbers because they are triangles. This is a triangle. And this is called a trapezoidal number. Whoa. Well, trapezoidal number. Okay, so what does this have to do with the problem? Well, I'm glad you asked, because we are actually adding 2 trapezoidal numbers to find the solution. So let's code what we, so yeah, realize that this is, so the triangular numbers are a special case of the trapezoidal. So we only need to have a function for the trapezoidal numbers, which, like we said, is this and b minus a plus 1. You have to realize that the product is always even, because these numbers have to have different parity. Because here a plus b has the same parity as b minus a, but when you add 1, you change the parity. So one of them has to be even, and that's why this is always evenly divided by 2. So how many? So let's figure out what our b is for the first part, the triangular number, and that's going to be either k divided by 2 inclusive, or it could be that n is less than that, so it's also limited by n. So that's going to be our b, and a is going to be 1 here. So that gives us our first triangle, and then we need our second, which could be 0, because like we said, if it's n, if it's limited by n, then this is going to be 0, but it's going to be okay because we're gonna make it work, trust me. So then we know that a has to be k, because this is the part that starts from k and on, and then we need to figure out what this is, and we want, what do we want here? The minimum. So k minus 1 plus n minus b. So yeah, well, let me explain this. So on the one hand, the numbers that we need to subtract the b numbers that we already added in the first part, and that is n minus b. Okay, we put b numbers, and the remaining numbers are n minus b, right? And let's see the edge case like we said. What if we only need one number? So what if this is 1? If this is 1, then this has to be k. It has to be t of k and k. But in this case, it is k plus 1. So we need to correct it by subtracting 1. And that should work. And there's an edge case here. This is what I said about making this work. If b is n, which means that this must be 0, there won't be any numbers in this second part. This means that this is 0, and here we'll have t of k and k minus 1. So that's weird, because we assume that a was less than or equal to b. But here, the number of elements in the range is going to be 0 in this case. And then this is going to be, the whole thing is going to be 0. So it's going to work out. So let's try it out. And we get the examples right. And accepted. Cool. So yeah, I think it was a very educational way to solve it. These trapezoidal numbers come up sometimes in harder problems, so it's good to know them, and it's good to, and this comes up all the time, it's good to know how to derive it, how to visualize it. So cool. And we also broke down the analysis of this problem by doing a case analysis, thinking about the numbers that were greater than or equal to k, and then the other numbers. So we've seen some problem-solving strategies as well. So I really like this problem. If this was bigger, then it could be a harder medium, I guess. It's not enough for a hard these days, I guess, but that's fine. Okay, so let's move on. You're given an integer, and so maximize the profit as the salesman. Line number from 0 to n-1. You're given a 2D integer array. Okay, so this is an array of triples, indicating that the ith buyer wants to buy all the houses from start to end for gold of I amount of gold. As a salesman, your goal is to maximize your earning by strategically selecting and selling houses to buyers. Return the maximum amount of gold you can earn. Know that different buyers can't buy the same house, and some houses may remain unsold. Yeah, when I read this problem, it's a little ambiguous, I think, because I think if you choose a buyer, the buyer has to buy all the houses in the range, and then if another buyer wants to buy any of those houses, you cannot choose it. You cannot sell to it, even. Yeah, I mean it's not well specified, I think, in the because you could imagine that you could sell the remaining houses or something like that, but no, I mean they make this offer and it's all or nothing. So I would prefer if they specified the exclusion more explicitly. So constraints. Always look at the constraints. You cannot choose an algorithm without knowing the constraints. There are up to 10 to the 5. These are the houses. Yeah, these are the houses. So maybe this doesn't matter that much, but the offers are 10 to the 5. And yeah, so the ranges are constrained by 0 and n-1 and so on. And the goal is very small. I don't know why that is. My solution doesn't mind, I think, about any of these numbers, just this one. But okay, so how do we think about this? The structure of this problem is very familiar. If you have done DP problems before, you're asked to find to select a subset of these offers with the maximum sum of gold, subject to some constraints, to some restrictions. So this should already ring a bell. That this is a kind of a subset DP, or some people call it take it or leave it DP. because if you select, you can go from in some order. You decide whether you take an offer or not, and that adds some gold, the gold of that offer, to the total, and you decide whether you take it or leave it depending on the best choice for that suffix. And that means that it has optimal substructure. The solution, the best solution to a problem is the best solution to the subproblems. So it has all the tell signs of a DP problem. However, there is this catch that there are dependencies between what you can take. If you take one offer, then it could be that conditions your next choices. It could be that there are some choices after that cannot be taken because they would intersect with the one that you took. So we have to deal with that. And how do we do that? So let's say that we are considering the ith offer, which let's say that it's start I, end I, and gold I. And so more visually, this is going to be some range in the line, and so let's say that we know we can take I. We can take it or leave it. We know that it doesn't conflict with any other of the previous choices we make. We want to find the maximum gold for the suffix from I till the end. And so how do we discard all the ranges that intersect in the case that we take the ith range? We need to discard somehow all the intervals that intersect with the ith range. And one way, whenever you have intervals or ranges in a problem, you have to think a common tactic is to sort them either by start or by end. So let's try first to sort them by start. So that means that if we sort them by start, all the ones that are after the ith position have to start either here. So this is, let's draw a line actually. So this is start, and this is end of I, and so let's classify them in two groups. The ones that start here and the ones that start from here on. This is the next element, end plus 1. Okay, and this is pretty clear because the ones that are in red we cannot choose, and if we take the ith but the blue ones are not in conflict with A, so they're still available. So that's very convenient, because since we sorted by starting position, all the ones that are in red will be in an interval right after the ith. It could be empty, of course, and so we have to make a jump from, if we take the ith, we have to make a jump to here, to the first start that is after end of I. Okay, so that's all. That's the way to deal with the conflicts. So let's write down, like we did the other day with the contest, let's write down a formula for this recurrence. So we have, let's say that we have gold. The maximum gold starting from the ith position of the offers, sorted like we said. So we have a base case, which is when I is equal to n, where n, well, it's not the n, it's the number of offers, okay? In that case, we can get 0 amount of gold. And then, since this is a take it or leave it kind of problem, we have, so this is otherwise, if I is less than n. So we take it or leave it, and we want the maximum of those. So if we leave it, then it's easy. We just get the maximum gold from I plus 1. Okay? But if we take it, we gain the goal of I plus all the gold we can get, but starting from, and let's imagine that we have a function that does this. We call it next, and we want the next index of the offer that starts after end of I. Okay, and these are 2. And then again, it doesn't have to compile, but let's keep it tidy. So yeah, this is it. We need to figure out what this next thing, we can do a binary search for this, because like we said, we sort them. So that next is going to be a binary search, and in Python is bisect, the bisect library function. So let's do it. So we said we want to sort for the start, which is the first component, so we don't have to do anything else. And then we want to do a memoization, so we add the cache decorator. And then we want this, which is the max profit or max gold, I like to call it. And the only variable is I. The base case was if we're at the end, to return 0. Then we have 2 options. So let's unpack. I don't think we need the start. We need the end of I and the gold of offers of I. And one option is to leave it. So in that case, we get the max gold. So this is pretty much the same that we wrote there. At the end, we're gonna return the max gold of starting from 0. And here we want to add the goal, and we need to figure out where we start. And like I said, this is the next function is going to be bisect left Well, let's think about it. So we need to search in the offers array, and we need to search and, but there's a catch here, because the elements of this list are lists. So we need to, end is just a number, so we need to pass a list to search, and lists are ordered lexicographically. So that means that if there's any listing here that starts with end, then it's gonna come after these elements, and we don't want that. We want to skip the ones that start with n, because that is considered an intersection. So there are two things. We can just add one here, that should work, or we could do bisect right, I think. But let's do this. Offers. Where did I write offer? Here. Again. Okay, here. Wow. Sorry for the typos. Too soon. 3 and 10, that's good. And accepted. Cool. So yeah, I mean, it's pretty much what we did here, and I hope you like this explanation. Again, it's a visual way to understand. We're also classifying into things in two buckets. So that's all I have for this one. And let's go to the last one, to Q4. Share the link. Find the longest equal subarray. This is a medium this time, it's not hard. So this was a easy medium kind of contest. That's why some people finished very quickly. It was like a typing contest for people who are very advanced and who had already solved these problems before. But that's okay, don't worry about it. This should be set by default, by the way. Anyways, so you get an array of integers, nums, and an integer k. Subarray is called equal if all the elements are equal, and the empty subarray is also an equal subarray. Return the length of the longest possible equal subarray after deleting at most k elements from nums. Subarray is a continuous, well, okay, the usual subarray definition. We have a few examples here. Here the output is 3 because yes, I guess it could be this, which has 3 elements. No. How is this one? It's at index 2 and 4. Yes, so you get this. The deleting them. Longest equals subarray starts at. Oh, so you don't have to count the ones that are deleted. So you count the threes. Okay. Can be proven. Alright. And here k is 2, so you delete the 2 2s and you get the 4 1s. And that's why it's 4. So it's pretty clear, and okay, so you have up to 10 to the 5 elements. So that usually means that you can't do a quadratic algorithm to solve this. That's the usual size to communicate that. So we have to do something linear probably, or n log n. Alright. So this is a very familiar problem to me. So there are many. I've seen this kind of problem before that can be solved by 2 pointers or by the sliding window technique. I like to call it 2 pointers. But there is a catch, because if you don't know what, once you know which number it's going to be repeated, it's going to be counted, then it's a very standard sliding window problem. So in that case, the array gets binarized in a sense, well, pretty explicitly, because if you already know which number it's going to count, then any other number, it's the same. You don't care if it's a 1 or a 2. You have 3s. If you know you want to count 3s, then you have 3s and non-3s, so it's binary. And that is important because if you keep your sliding window and you count the numbers that are not 3s, when you slide it to add an element to the right, then it could be that the non-3s exceed k, and in that case you need to move the left side, the left pointer, to the right as well. And you never need to move it to the left, because you know that before moving the right one position, the condition was valid, given, meaning that the non-3s were less than or equal to k, so it cannot decrease when you add one element to the right. And that is the condition that you need. You need to make sure that when you advance the right pointer one position, the left pointer cannot need to move to the left. That is the condition. Maybe I can draw what I'm saying a little bit. But so how do I draw this? Let me think. Yeah, so this is the array and this is the right pointer. Hello, that LeetCoder. How's it going? My man. So here you have the left pointer, and let's say that you just advanced the right pointer from here to the next element, okay? And the left pointer was here, so the number of elements that were non-3 or let's call them bad, the count of the bad elements, we know that they were less than or equal to k. Okay, because that's our given. And now we want to extend this to include this new element. Okay, so that means that we want to increase bad if this is a bad character, and now maybe bad is greater than k, so we want to move left to this size while bad is greater than k, and that's a standard sliding window or two-pointer code. So the question here is, how do we know which number we want to count? That's a million-dollar question here, and the answer oftentimes is we don't know. We just try them all. Whenever something is bothering you, you can just try to fix it. But you might think that you cannot do that because you will have a quadratic algorithm if you do it. But it turns out that you don't, and that's the interesting thing about this problem, because for every, so you don't need to go, when you do the sliding window, you don't need to go over the gaps, over the elements that are bad, as we call them. We just need, you can do it just by going over the numbers that are good. And so that means that your total number of iterations, this is going to be two nested loops, but the total number of iterations is going to be the total number of characters, or the total numbers of elements in the nums list. And that means that it's going to be linear, okay? That's pretty interesting. So let's do it. So first we want to do a group by kind of code. We want to, for every different value, we want to save the positions in order that they occur. So this is usually done with some kind of a dictionary. In Python, we can use the default dict, and we want to append to a list the indices. So we want to have the index and the value, and we want to append the index for that value, and then we want to go over, we don't care about the value anymore now, we only care about, we can drop it, we only care about, well, no, don't confuse it with this value. What I mean is that this E number that we're using as a key is just for grouping. Now we don't need it anymore. And so we're gonna keep the overall best length, which is 0. 0 is valid because it says that an empty subarray counts. So you should be aware of what the when you want to maximize or minimize, think about what the default value could be, because sometimes you put 0, but it turns out that it could that it's not valid, and you end up with a wrong answer. So okay, and so we're gonna do the usual left-right pointer in the range length of A, and here, so even though we don't care about the values of the let's call them gaps, we don't care about the values of the gap, we only care about the quantity. So when we extend the window, we add one element to the right, we want to see what the gap was for that. And for that, and we're going to do the same for the left pointer. So let's write a function that computes the gap for for some I. Yeah, let's do it this way. So we want I plus 1 minus A of I. So remember, these are the positions of consecutive elements. So this is the gap, but here we're counting the distance, not exactly the numbers in between. If they are consecutive, we're going to get 1, but we want 0 if they are consecutive, because it's an empty gap. So we have to subtract 1. And we want to keep track of all the gaps, of the amount of gaps in the window, which is initially 0. And there is a catch, because here at the beginning there is no gap. So we only want to add the gaps if this is greater than 0. And here we want right. No, we want right minus 1, because we're adding 1 here. So this is going to compute the gap between I and I plus 1. And now we do the usual, while the gaps are greater than K, which is what we said, then we do the same, but with the left pointer. And here we do want left, because this is going to be left, the gap between left and left plus 1. So it makes sense, and we increase this. We do that until it is valid, and finally we get the maximum, which is the number of elements in this range inclusive, and that should make it. 3 and 4 makes sense, and accepted. Cool. So yes, here it was the idea, and maybe now you can see clearer what I said about this being linear, because if you think about it, how many times does this piece of code executes? How many iterations of this loop are we going to have? Well, for each group, we're going over all the elements in that group, but the total number of elements in all the groups, it's the size of nums, which is the number of iterations that we did here. Each element there was an element that we added to some group. So that's why this is in total it's going to be the size of nums, and that's why it's linear. This is going to be executed the number of the number of groups, which is also bounded by nums, and this is a standard sliding window code, so we know here that this is linear again, because we are always incrementing the right and the left pointers, so that means that at most we're going to do 2 times the size of A iterations. So that's why this is all linear, and it's a cool problem. I think I solved it once. I think there are versions where the numbers, instead of numbers, you get a string, you get characters. And I think that in that case, you don't have to be clever with this. You just can brute force all the letters. So I like that this is a better problem, because it makes you think about this idea, which is interesting. So yes, that is all I have for now. I hope you learned something from this. I think I made it pretty visual, intuitive. Also, I tried to prove the claims that I made and the strategies that I chosen. I tried to go over the problem-solving strategies. So yes, that's the style of streams that I want to make. I want to help you learn things that are more general than just a specific problem. So that you learn to think about these problems, you learn to problem solve, you learn to solve problems in general and not just one specific problem. So that's my goal. I don't know if I'm gonna succeed, but I'm trying. So your feedback is always welcomed. I want to improve. So I hope you like this one, and I'll try to stream tomorrow. I'm still behind schedule with 2 contests, I think, the bi-weekly and the last weekly. I'm gonna be doing another. I'm gonna be doing streams for those 2 as well. I think on Saturday I did for the previous weekly, the 358. I recommend you to watch it if you haven't already. And then I'm gonna be doing sometimes I do streams for particular problems that I find interesting, that I think I had some value. I also did a stream explaining segment trees with this kind of style of drawing things out. So yes, that's my content. Thank you for your support, and see you in the next one.